I'm Guillaume de Giovanni, co-founder of Viqthor. Well, this is the first exhibition about engineering activities around quantum, and especially quantum computing for us. So it was important that we participate in this first edition. So we address superconducting and spin qubits quantum computers, and we do what people say is control electronics, where we add a little flavor to it because we add photonics. We are the first company in the world to drive superconducting qubits with fiber optics. This place in particular in the exhibition area is called the demo zone. So the topic here is to demonstrate real systems. How do they operate for all the visitors, the attendees, to be able to witness and try our hardware. Because we manufacture hardware. Usually you have a lot of people talking about their activities, but not demonstrating hardware. So getting the hands on the equipment, getting to play with it, is a big advantage because they don't have to come to our facility or we don't have to visit them. We can show everyone how our system works. So here we have a system that has two main sections. The first one is, I would say, the electrical section that generates and measures waveforms. So typically to drive a qubit, we will send signals and measure the response back. So we do this electrically with our software. Here, for example, we measure what we call a time of flight. It's sending a pulse to the qubit and measuring the time it takes to come back. And we are going to do it two ways. One way is fully electrical because we send the signal in an electrical way, and the other way is going it on fiber optics. So we send the electrical signal to a fiber optic converter that will send it optically. And we measure here the difference between the time of flight electrical and optical. And the idea is actually to demonstrate the quality of the signal, the way that, yes, you can scale up a quantum computer using photonics. Quantum computers will bring a lot of computing power to the supercomputers today. Today, you have limitation. Things, you cannot simulate physics as closely as you would wish. But with quantum computers, because it is quantum, you will be able to simulate the physics of materials, of atoms, of chemicals, of drugs, with a very high precision. The future is a long way of engineering. So not only physics has to make progress, but engineering also. Because if you think about a quantum computer that today has maybe 100 qubits, this is not enough to do real computation. So we have to scale it up to, let's say, 10,000, 100,000, or millions of qubits. And if today you need like 4 cables per qubit, this is not going to work in a cryostat. So we, on the side of the control electronics, have a lot of work to do to prepare actually the electronics, the control systems, so that QPU manufacturers, you know, those chips, the qubits manufacturer, they can grow their chip and have a system to control it and deliver the computing power. Physics is hard, electronics is hard, engineering is hard, but usually you can find solutions. It just takes time. The idea here is let's start soon enough so we will be ready for when the qubits are ready.